Intelligent life certainly exists within our galaxy. Therefore, the probability of intelligent life developing in a galaxy like the Milky Way is somewhere between 0 and 1, but it cannot be 0. We are living proof of that fact. Even so, we haven't observed any other life forms except for ourselves. It seems like we're completely alone. If anything, the universe should be teeming with life. However, more than a century after the invention of the radio, humanity remains clueless. This absence of detectable intelligent life beyond our own inspired Frank Drake. In 1916, he summarized the main concepts which influenced the existence of observable alien life into one simple equation, now known as the Drake equation. But what even is life? According to the Oxford Dictionary, life is the ability to breathe, grow, reproduce that people, animals, and plants have before they die and that objects do not have. This definition is vague at best. There exist life forms that don't breathe, and there exist things that reproduce and grow, but aren't alive. For now, that doesn't really matter, as we'll consider something to be alive when it's able to use resources to grow or reproduce. After all, we don't know what aliens might look like. They can be anything from being almost human to planet-eating titans. The Drake equation can be regarded as a summary of the factors that affect the likelihood of us detecting intelligent extraterrestrial life. The main equation consists of 7 factors. Let's see what the formula means, make an estimation, and try to get a grasp of the magnitudes we're working with. For the first 3 factors, we can be more or less certain of their values, but for the last 4, we can only make an educated guess. That's why they are regarded as free variables that will eventually determine the outcome of the equation. The outcome of the equation is a number big M, which is the amount of civilizations in the Milky Way galaxy that we could possibly communicate with. The first variable, R star, stands for the average rate of star formation in our galaxy. This is very important because the civilization can only emerge around a star that radiates energy, which is necessary for the creation and expansion of life. Original estimates place this value at 1 star formed per year. However, in 2010, NASA and the European Space Agency went deeper and estimated that about 0.68 to 1.45 solar masses worth of stars are formed each year. Divide that by the average new star's mass of around 0.5 solar masses, and we may expect an average of 1.5 to 3 stars formed per year in our galaxy alone. The fraction of stars that have planets is represented by FP. This is almost certain to be near 1. NASA concluded that stars are orbited by planets as a rule, rather than the exception. The average number of planets per star that could support life, NE, also knows some fluctuations. The consensus was that NE had a minimum value between 3 and 5. However, further research pointed out that the answer isn't that simple. Based on data from the Kepler space mission, there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of stars. That sounds like a lot, but this would draw NE back to roughly 0.4, as there are about 100 billion stars in our Milky Way alone. We're not done yet. These estimates only focus on the position of planets, but the position of a star system is as important, due to supernovae having the ability to strip planets of their atmospheres if they're too close. In turn, if the supernovae are positioned too far away, planets might lack the heavy elements that might be essential for life. Furthermore, one factor that might bump up the value for NE is the possibility of life emerging on moons, such as Jupiter's moon Europa and Saturn's moons Titan and Enceladus. There are many factors at play that cause a lot of uncertainty, though not as extreme as the following variables. F1 represents the fraction of the planets that actually go on to develop life. On Earth, life began around the same time as favorable conditions arose, which suggests that the formation of life, or abiogenesis, is fairly common when the conditions allow it. However, we can't draw a solid conclusion from just Earth alone. That's why finding remnants of life on Mars or Europa would be such a groundbreaking discovery. It would imply a value for F1 close to 1, which would mean that the probability of other life forms existing somewhere in our galaxy would be almost 100%. That doesn't mean that this life would be intelligent though. This is where the factor Fi comes into play. Fi represents the fraction of life-harboring planets that go on to develop intelligent life. This is perhaps the most controversial factor in the equation. Arguments could be made for a value close to 0 or a value close to 1. Famous biologist Ernest Mayr stated that a value close to 0 seems likely because there exist billions of species on Earth, yet only one became intelligent. But those who favor a high value will point out that life generally increases in complexity over time. Thus, intelligent life is an almost inevitable outcome, although finding primitive life on other planets like Mars would be great for the value of F1. It would be bad news for Fi, since it would mean that the only life forms we found died before ever developing intelligent life. Since the value of N represents the amount of civilizations with which communication is possible, a new factor is needed. FC represents the fraction of intelligent life that reveals its existence by sending signals into space. It's difficult to give a good estimate of this number. Approximations go anywhere from 0 to 1. Intelligent life developing communication technology that emits signals into space seems pretty likely, but this technology might also become obsolete very quickly. Using radio waves could be a primitive, rarely used method of communication to them. How long these civilizations send signals into space is quantified by the factor L. One of the first estimates was made by American science writer Michael Sherman, who estimated L to be around 304 years. This guess was based on the average duration of historical earthly civilizations. However, when one civilization falls, let's say the Roman Empire, another one would take over. This civilization could then build on the previous one, and we would then have to introduce a reappearance number. But for now, let's discard that number, as it is only based on civilizations that never reached interstellar communication. Another argument suggests that once a civilization has developed enough, it overcomes all threats to its survival, thus placing the value of L in the billions. This causes one big problem. N would possibly become infinite, so we'll have to find a better alternative to L. One proposition is a substitution of L with FIC times T, with FIC being the fraction of communicating civilizations that become immortal, and T representing the length of time during which this process has been going on. The Drake equation has very close ties to the Fermi Paradox, which is the inconsistency between the lack of evidence of advanced extraterrestrial life and the apparent high likelihood of its existence. The paradox owes its name to the physicist Enrico Fermi, who blurted out the phrase, "But where is everybody?" when talking about aliens with his fellow physicists back in 1950. Today, many explanations to this question have been proposed. In terms of the Drake equation, these explanations can be put into three distinct types. The first type of explanation blames the lack of aliens on the difficulty of intelligent life developing, which corresponds to a low value for the first 5 terms in the Drake equation. This would mean that as a civilization, you have overcome a great filter, which is a barrier that is difficult for life to overcome. This type of explanation is rather positive compared to the second type, which implies that there is a great filter ahead of us, which has wiped out almost all other intelligent life. This filter could be something like a special virus or a planet-destroying AI that will eventually be invented by all intelligent civilizations. This means that the value for L would be small. The last type of explanation puts the blame on FC, meaning that intelligent civilizations that do exist don't typically broadcast their existence into space. We found many different values. Let's now make 2 different calculations, one pessimistic and one optimistic, so that we can have a full range for possible values of N. Let's start pessimistic. We found that our star lies between 1.5 to 3, so let's take 1.5. The formation of life on Earth could have required an extremely improbable rare set of combinations. Therefore, one of the lowest estimates for the value of FB times NE times F1 is a tiny number 10 to the negative 5. If we then use Ernest Mayer's view on intelligence rising, we get Fi equals 10 to the negative 9. Drake himself calculated FC to be around 0.2, which is a pretty low estimate. Let's also be pessimistic for L and guess that the average civilization only lasts for 100 years. Pour everything into the formula and we find N to be 3 times 10 to the negative 13. This is a stupendously small number that essentially tells us we're alone in our galaxy, perhaps in our universe. Now, let's be very optimistic and use the upper bounds of the estimates. Our star is now 3 years, we find FP to be 1, NE is 0.4 based on NASA's Kepler mission, F1 is also 1, as is Fi and FC. They're all probabilities ranging from 0 to 1, so they might as well be 1. L is now 10 to the 9th years, because the civilizations could have essentially become immortal. portal. Let's multiply everything again. Now n equals 1.2 times 10 to the 9th. This means that we would have 1.2 billion communicating civilizations in our galaxy alone. So where are they? Well, perhaps one star system away, perhaps a few hundred light years away, or maybe there's only one at the other side of the Milky Way. Perhaps there are none. Tweak the numbers a bit and everything changes by several orders of magnitude. It's a probabilistic argument without a definitive answer. We have so much ahead of us left to discover before we can come even remotely close to an answer. For now, we only have an idea. Therefore, one shouldn't regard the Drake equation as the solution or the answer, but rather as a list of concepts scientists have to bear in mind when searching for life. It's a roadmap of what we have to learn before solving the everlasting existential question proposed by Enrico Fermi. But where is everybody? For now, we remain clueless, as this galaxy does not seem to be teeming with alien life, because we haven't received extraterrestrial broadcasts yet. But maybe we might be looking in the wrong places. Alien civilizations might have long surpassed radio communication, and to them, we'd just be speaking gibberish. For now, we don't know, but if you want to learn how to know, this video just might be for you.